Right. And hello again. Okay, what I wanted to do in this lesson is do the CH3062, which is the acids and bases. Now, did you do level 2 chemistry last year or not? No, you didn't. Okay, so um, I'll try and sort of recap that a lot more while we go through. So the first thing is, if we're looking at acids and bases, what is an acid? How would you describe it? It's a donator of H plus or protons or hydronium ions. Yep. So that's acids and solutions, and that's what we call is the Arrhenius definition. That acids, when we put it into water, will release hydronium ions, and bases, if we put those into water, what do they release, according to Arrhenius? Hydroxide ions, correct. Okay, and really that is the main definition that you're going to be using at level 2 and level 3 chemistry. Lowry Bronsted is a slightly different definition. It talks about a proton donor and a proton acceptor, but if you think of what is H plus, hydrogen atom is one proton and one electron. So if I remove an electron to make H plus, it's just a proton. So if you're donating a hydrogen ion or if you're donating a proton, it's the same thing. Hi, Johnny. Okay, so we just did the basics of what is an acid and what is a base. Now, if you do have an acid, there are two things, or a base, there are two things you need to be aware of. If I put it into solution, not all acids will totally give up all their protons they have. So we talk about strong acids and weak acids, as well as strong bases and weak bases. So what do you think a strong acid is? So some of you are typing. I actually also meant to get a FET simulation up, so I'll just quickly do that now. Yep, so it dissociates completely, correct. So a strong acid will totally dissociate, so totally give up all its protons, okay, or hydrogen ions, and a base would totally ionize or dissociate to get rid of all its hydroxide ions, or it's broken up completely, so it forms an equal amount of hydroxide ions. So I just wanted to get that one up so we can have a look at it. So if we have a look here, what we have in the first place is water, okay, because that's what's listed over there. Now water will collide with another water molecule, and a tiny amount, not very much, will break up where one water molecule grabs a proton from the other water molecule. So you can get the hydronium ion and the OH minus. So that's always going on in the background, but it's not very much at all. It's 0.0000001 moles per liter of hydronium ions and hydroxide ions. So it's just a tiny, tiny little bit, but it's there, okay? And it's important that you remember that, because when we ask you what sort of ions are in solution, you've got to remember water always has those two ions in solution, hydronium and hydroxide, even if it's totally neutral. If I have a strong acid, okay, so HA is my strong acid. So an example of a strong acid is HCl. If I put HCl in water, it dissociates completely. So it gives off all its hydrogen ions, We call them hydronium ions because, as I say, you're not going to get an H plus floating around by itself. It's just too reactive. It'll get attracted to something. So we represent it as H3O plus. And we're left with the anion. And notice the arrow, it goes all the way to the right. It dissociates completely and there's no back reaction. So when you look at what we've got here, you've only got the blue anion, and you've got the water molecules, well, we don't show the water molecules, and the hydronium ions. Do we have equal amounts of hydronium ions and anions, from the acid? Okay, Caleb, you said no, and it is a little bit of a trick question because it depends on what you mean by yes or no. So you are, in a way, both correct. Johnny is correct in that they are approximately equal, because for every HA that breaks up, it's going to give one A minus and one hydronium ion. So they're approximately equal. But as you're also right, Caleb, in that there's going to be this tiny, tiny little bit amount from water that's dissociated. So if you like, this one is going to be tiny, tiny, tiny bit more. But it's enough to ignore. So we can say they're equal. Okay. Right, so if I looked at the pH, if I've got lots of hydronium ions present, okay, I get quite a low pH. Now, do you know how we calculate pH? What is the formula for pH? Negative log of the hydronium ion concentration. Correct. Okay, so the more hydronium ions present, because it's a negative log, the smaller the pH. They go opposite. So the bigger one is, the smaller the negative log is. Okay. If I now change this to a weak acid, so HA is now my weak acid, so it's like carboxylic acid, like ethanoic acid or methanoic acid or so on, and I'll put that into water, then do you notice we have an equilibrium arrow? It's the equilibrium arrow shows the reaction hasn't gone all the way to the right. It's sort of sitting somewhere in the middle of the reactants and the products. Well, when I say middle, it doesn't have to be the middle. It could be, in fact, something like ethanoic acid. Only 3% of it will actually dissociate. The rest stays CH3000. So middle is, if middle is 50%, this is just going tiny little bit over to the right. Okay, so we only get a few anions present and a few hydroxide ions present, but lots of HA. So in the previous one with a strong acid, there was nothing grey there for the HA. For the weak acid, notice that if you had to say what's in the biggest quantity, what substance would it be? HA, A minus, or H3O plus? The HA. Okay. If we asked for the water to be put in, then obviously water is going to be in the biggest amount. Okay, there's about 55 moles of water per litre. But if we ignore the water, then most of it's going to be HA, and then we'll have approximately equal amounts of A minus and H3O plus. What do you think would happen, and notice with the pH, because I've got fewer H3O plus ions, the pH has gone up. Okay? If I now do the strong base, okay, so what we've done is the metal, which is grey, and then OH, which is grey. I think they could have made those different colors, but anyway, so they made one plus and one minus. So this would be like calcium hydroxide or sodium hydroxide or potassium hydroxide, okay? And when it is put into water, what dissolves will break up completely. So I know calcium hydroxide isn't particularly soluble, but whatever does dissolve will form calcium ions and hydroxide ions. We won't get calcium hydroxide as some sort of molecule dissolved in the water. Does that make sense? You're either going to have calcium hydroxide as a solid and calcium ions and hydroxide ions. You're not going to have calcium CaOH2 somewhere floating around. Okay. So anything that, if it breaks up as a strong base, you're going to get the cation and you're going to get the hydroxide. And if you have a look, it's got a pH of 12 because we've actually got very, very, very little hydronium ions present now, and it's mainly hydroxide ions. And notice we've got no MOH, it's dissociated completely. But if I go to a weak base, notice the equilibrium arrow, notice I've got, we've ignored the water, we've got the base, we've got the base that's accepted a proton, and we've got the hydroxide. We'll be going over these equations so that they will make more sense to you. Okay, so what species is there in the biggest amount? The B, the BH plus, or the OH minus? The B, correct. So whenever you've got a weak base or a weak acid, it's always going to be the weak acid or the weak base that's going to be in the biggest amount. And the little bit that does break up will be equal amounts, but they'll be smaller amounts. So a typical question is where you get given a substance and you have to say what species are in solution and rank them. So, you would say B is the most because it's a weak base and so doesn't react with the water very much, and so most of it remains undissociated. Okay, then you'll say there'll be equal amounts of BH plus and OH minus, because for every B that reacts with the water, we get equal amounts of, BH plus and OH minus. Okay. The other thing they will ask around this sort of question is the pH. So if we have a weak base, then we don't have as much hydroxide in solution. So the pH will still be alkaline, it'll be above 7, but it won't be very high. This is assuming all similar concentrations, because obviously the more dilute the solution, the less hydroxide and hydronium ions will be present. Okay, so I see Caleb is typing, but I'll answer that when it comes up. The other thing they can ask you is about conductivity. Now, what do you need to conduct electricity? Ions. Correct, Johnny. Right, Caleb, why are the two terms basic and alkaline? Basic is anything that has a pH greater than 7. Okay? Alkaline is a base, but it refers to soluble bases only. So, in a way, if you've got calcium hydroxide, it's not particularly soluble. So you'd call that a base rather than an alkali. So sodium hydroxide is a base and an alkali. Calcium hydroxide is a base, but not an alkali. So it's just to do with solubility. But both of them mean pH greater than 7. The alkaline has just got one extra step. Yes, so an alkali is a soluble base. Correct. Yeah. Okay, so if I put this in, right, and we said we've got ions present, have a look at my light bulb there. It's sort of glowing not too badly, but I'm going to click through these quite quickly, and I want you to see how much that glows, okay? So there's water, there's strong acid, there's weak acid, there's strong base, there's weak base. So let's start off with water. It's barely glowing, okay? Why is that? There aren't very many ions in solution at all. There are very few. Tap water actually does glow simply because of the amount of chloride and other ions that are in solution. But pure water has such a teeny amount of ions it doesn't really conduct. Yeah, Caleb, it does depend where you are. But even mountain water, clean, fresh mountain water will still have dissolved ions because the water from the rain percolates through the soil and dissolves substances. Rainwater would be perhaps the most neutral. Okay, strong acids. Why does it glow so brightly? Lots of ions. So you would, when you're explaining this, you would say, say this was HCl. So you'd say HCl is a strong acid, so it dissociates completely to give hydrogen ions or hydronium ions and chloride ions. So there are lots of charged particles to conduct electricity and carry the current. So it's got a high conductivity. Okay, so you do all those sort of steps. If I have a weak acid, it doesn't glow very brightly. Why would that be? Not so many ions. And good that you're both referring to ions. Sometimes students, they get so fixated on the hydronium ions that they talk about hydronium ions for both pH and conductivity. Now notice it's only the hydronium ions, or the hydroxide, for pH, but it's any ion in solution for a conductivity. Sorry, I went blank there. Okay, strong base. We again have got lots of ions because by definition a strong base dissociates completely to form the hydroxide ions and the cation. Okay, so there are lots of ions in solution, so it will be a good conductor. And then of course the weak base only partially dissociates, so will not have very many ions in solution. Okay, and then so you can play around with this. This one's a nice one in that it'll work on an Apple, it'll work on an iPad, it'll work on a normal computer. So it's a good one to play around with. You can see the equivalent amounts. This is the other thing that they tend to do is you might get a graph in the exam where they'll say here's a graph, with so much, state what each column of the graph represents. So you would have to have a look and you'd say, right, we've got, they'd have to sort of tell you that it's, say, ammonia that you've put it. Yeah, okay, John, it is different in the book simply because when I wrote that book, they didn't have the HTML version, they had the old Java version. But Java doesn't work on very many computers now because of that security hole. So use the HTML. Yep, the HTML ones are actually very nice. Okay, yeah. Okay, I know we're so busy always rushing into some other thing that I'll never have time to update the ones that we presently have. Okay, so if I said you had ammonia is a weak base. So you would have to say what these substances are. Actually, I might go to say let's do a strong base first. So here they've made it orange and purple, so you know which matches. But if I said you put sodium hydroxide into solution, here's a graph, tell me which column is associated with which ion. Okay, so you wouldn't have any sodium hydroxide present because all the NaOH is broken up completely, so you never have any NaOH as one. You've got Na and OH as separate. So notice you have equal amounts. Okay, and then what you don't have, but there will be a tiny little bit over here, and that is from the dissociation of water. So what other ion would be present in an aqueous solution? The H3O plus. So because of the dissociation of water, you're always going to have these amounts. Okay, but you can see it's 1 times 10 to the minus 7. It's not very much at all. So if I go to, where was our strong base? So Caleb, You said the OH should be slightly higher, and that's true. The thing is, if I try to make this like added sort of 10 to the minus something, because this 10 to the minus 0.01, and if I added then 0.0000001, it doesn't actually make much difference. But yep, so always just say approximately equal, and don't try and make it exactly equal, or exactly a little bit higher, because you're never going to get it to scale. Okay, so this diagram doesn't show it, but you should always state that hydronium ions are also present, but it's only going to be a tiny, tiny, tiny amount. Okay, strong acid, I'm not going to have any, so say HCl, I'm not going to have any HCl present. It'll only be present as hydrogen ions and or hydronium ions, sorry, that's the orange, and the anion. Okay, and there's your water. Can you see it's 55 moles per liter? So you got most of the water there. Now, if I have a weak acid, because it hasn't dissociated, I'm going to ignore the water, because obviously we'll always have most of water. We'll have most of HA and equal amounts of the A minus and the H3O plus. And we will always have a little bit of hydroxide. And then the weak base, but I think this is often more useful if I had it, wrote out for ammonia. My ammonia would react with water and it forms actually ammonium hydroxide, ammonium NH4 plus and hydroxide. So I will have equal amounts of ammonium and hydroxide, but I'll have most of mine will still be as ammonia. Okay, so you think you'd be able to explain conductivity and you'd be able to explain pH. Yep. Okay. Right. So what do you need to know? You do have to learn some acids and bases off by heart. And I meant to actually get this up straight away. In a 91392 assessment normally there is, so this is just the NZQA site, and there normally is I can't see it at the moment on here. It tells you what acids and bases you need to know. So assessment I'll just go to the so exam specifications. So that's what I wanted, exam specifications. And notice, I'll make this bigger so you can see. These are the ones they expect you to know for this exam. So they won't tell you whether it's strong or weak, because you are supposed to know it already off by heart. Any other acid that's not any of these, acid or base, they will have to tell you whether it's weak or strong, or they would give you the Ka, because they only give Kas for weak acids. So which ones are strong acids that you have to know off by heart? HCl, HBr, nitric acid, and sulfuric acid. So perchloric acid is also strong, but you don't have to know that one off by heart. They would have to tell you it's strong. Okay, strong bases you have to know is KOH, so potassium hydroxide and sodium hydroxide. So if they give you potassium hydroxide, you are supposed to know it's a strong base and it dissociates completely. If they give you sulfuric acid, you are supposed to know it's a strong acid and it dissociates completely. Okay, weak acids. What you're supposed to know is HF. So if they ask you to compare HF and HCl, in terms of conductivity or pH or something like that, they would you are expected to know that HF is a weak acid. Yep. So you're given 3 weak acids you have to know. HF. HF, by the way, is weak, but don't forget it is pretty potent and can cut through glass as well. Fluorine and HF. It's not something you contain very easily, even though it's a weak acid. So ethanoic acid and ammonium. So if they say ammonium chloride, to me that's a salt, but it did come up in one exam and they wanted weak acid for it because of ammonium. Okay. They didn't give you the choice of salts because you had to choose which one. So, if you knew your stuff, if salt wasn't there, you would have chosen weak acid. These are the weak bases you have to know. So ammonia, then this organic compound, which hopefully you will all know after we've finished all that organic. You can either, the proper name would be methanamine, or the old name would be aminomethane. And then, of course, the ethanoate, which is the conjugate base of ethanoic acid. Now, I haven't used that term conjugate yet. I will talk about that very soon, so just keep it in the back of your mind. Okay, so that's what they said here. Less familiar weak acids and bases could be included, but, they'd have to tell you it was that. Okay, so there's your list for the bathroom door. It's not too bad. If you've already done level 2, you should actually know most of them. And you know that all the organic acids and bases tend to be weak. So ethanoic acid is organic, so it'll be weak. Methanamine is organic, so it'll be weak. Okay. Right. So if I now look at these, okay, as I said, this one over here, perchlorate, is strong, and I'd have to tell you it's strong. But if I was ionizing it, okay, then would you expect this to go pretty much totally red? Because the more ionized it is, the more red it goes. Or would you expect it to be only with a few red dots here and there? So, okay, partly, totally red, so more red, and there you go. So pretty much everything has ionized. Okay, compare phosphoric acid. Okay, if I ionize that, it's like the opposite. In fact, most of it has not changed, ionized, because we can see quite a bit of white there, and not very much. Ethanoic acid, if I looked at that, that's an even weaker acid, because notice there's even fewer hydronium ions. Every red spot's like a hydronium ion. What do you think for this one is methanoic acid? Do you think methanoic acid, would it be similar to ethanoic? Yep, okay. So if I do that and ionize, it's pretty much the same. Okay. HCl, what would you expect for HCl? Because this is the ones you're supposed to know. So it'll be more red, so it should go totally red. Okay. I mean, there's so little of HCl, we can ignore it. Okay. Nitric acid, the same thing. We would also expect it to go totally red because it's also a strong acid. Okay, so that's just sort of like a visual thing, like the FET, to show you. Right, now, I did use the term conjugate. That is a word you should know. When a base has accepted a proton from, say, water, okay, it now has an extra proton. So it could go back, it could actually donate that proton and go back again. So we have this pair between the base and the protonated base, which can now act like an acid. Because do you see, if I protonated the base and then it goes back to form the base again, this species here must have donated a proton. Yep. So when we write any of these equations, there's like a couple there. The base with its conjugate, and that's the word we use. Conjoined twins or conjugal rights or something like that. You know, you can think it's like a couple, a pair, and so on. So you've got the base with its conjugate acid. Now, the conjugate acid has to be related to the base. So can I say that ethanoate is the conjugate base of HCl, for instance? No. Okay, ethanoate is a base, okay, and HCl is an acid, but there is no connection between them, so they're not conjugate. So when you get asked to write an acid base or conjugate acid base pair, then they have to be always be related, you know, where one has an extra proton and one, you know, doesn't. Okay, so for instance, that'll be the conjugate acid and that'll be the base. If I did a strong base, then this would be the base and the conjugate acid would be the M+. Okay, it doesn't really work very well with bases, but anyway, the weak acid, if that is the conjugate acid, then which of these two would be the conjugate base? The A-. Okay, and the same thing for the strong acid. So if that's the conjugate acid, then its conjugate base would be also A-. Now, as a sort of tip, the stronger the acid, okay, or base, whatever's on one side, the stronger it is, and by stronger I mean the more likely it will dissociate, okay, the weaker its conjugate base. So if I was doing an acid and its conjugate base, so for instance HCl is a strong acid, so Cl- would be the base. Now, is Cl- a strong base or a weak base? It's a weak base. It's very, very, very weak. It's so weak it actually doesn't really want to pick up any proton whatsoever. Because the moment it picks up a proton, it forms HCl again. And HCl in water is going to immediately break up and form HCl- again. So it's an incredibly weak base. It's so weak we consider it neutral. If I had, say, ethanoic acid, and its conjugate base is ethanoate, then it just simply depends where the equilibrium lies, but both of them will be weak, okay, but the weaker the acid, the stronger the conjugate base would be. Okay. Right, so that's just as a, you know, if you it's sometimes useful, like I know we use this in organic chemistry. If the leaving group was a chloride, it's such a weak base it doesn't really attack back again, so it's very hard to make the ethanol chlorides, whereas ethanol chlorides are very reactive and go the other way very easily to form hydroxides, carboxylic acids and so on. Okay, so that was that. So we've looked at strong acid, strong base, the effect on pH and conductivity. We've looked at conjugate acid and conjugate base. Okay, we've looked at what acids and bases you have to learn off by heart. Okay, now I want to get onto the reactions, because you're going to be writing a lot of equations, and very similar to what you did for your 3061 when you did the EEC method of equation, expression and calculation, we have something similar for acids and bases as well. Pardon me. Okay, so this is therefore the Ka. Ka would be the equilibrium constant when I write the equation as an acid. Okay, Kb is the equilibrium constant when I write the equation as a base. If I write it as an acid, what do you expect to see in that equation? So if you think of what makes an acid, so what would you expect to see in an equation with an Ka? H3O plus. So if you've got OH minus and you call it a Ka, you've gone wrong. Okay, it's actually very common where students get muddled about what equation to write, and then they just say Ka is equal to this, and there's an OH instead of an H3O plus. So always think of an Ka expression is to do with acids, so it must have hydronium in that expression. A Kb must have what in its expression? An OH minus. So if your Kb expression doesn't have OH minus in it, you've made a mistake somewhere. Okay. And remember what I said about the also strong acid as a very weak conjugate base and so on and so forth. And that's because if I've got HCl, the equation, now I can't actually just get H just by itself. The equation for HCl lies very strongly to the right. So I've got lots of products and pretty much no reactants, because remember the HCl by definition breaks up completely. So I've got, remember what my equilibrium is, it's products over reactants. So if I've got lots and lots of products but very, very few reactants, that numerical value is going to be very big, isn't it? I mean, if I've got 10,000 products and only one reactant, it'll be 10,000 over 1, won't it? So it's a very big number, so Ka would be big. If, however, I have a weak acid, so I put HF in solution, then not very much will dissociate. So of my, say, 10,000 molecules, I'm only going to have 50 dissociate. So I'm going to have 50 products over 9,950. What do you think Kb would be, Ka would be? Would it be small or big? Very small, because most of my stuff is lying towards the reactants and not towards the products. And so your Ka is going to be always quite small. Now we'll look at how this works. It's based on water, so don't worry too much on that. And the same thing with bases. You've got a very large Kb. It's so large we don't actually give you the value. The reason why we can't give you the value is because if we try and measure it in water, water is like an acid and base itself because it can form hydronium and hydroxide ions. So anything that dissolves in water and then trumps water, water is like the limiting factor. So we can't form Kas or Kbs from aqueous solutions of sodium hydroxide or any other strong base or any strong acid. So there's no value given for those. There are only values given for weak bases and weak acids. Yep, so for the conjugate base, the conjugate base is when it goes the reverse direction, and so it's going to be okay, I need to talk about the water first, so you can work out where this value comes from. If you multiply these two values together, so if I bring up the calculator, I don't know if you see it, so doing this first one, 7.2 exponential 4 negative, and I multiply it by the conjugate of the Kb, so it's 1.4 exponential 11 minus is equal to. Okay, and I'll just do that. Do you see that value is pretty much 1 times 10 to the minus 14? Okay. And if you did that for every one of these pairs, you'd get 1 times 10 to the minus 14. Oh, yeah, that's right. Okay, talking about the conjugate base of strong acids, yes, it's again, you can't really measure it because, as I said, the moment the chloride reacts with the hydronium ion, it forms HCl, which will immediately go back again to form the chloride and H. So, yes, so there's no values given for there. Certainly not for aqueous, because you can't actually measure it. Okay, so where does 14 come, in this whole acids and bases pH scale? It's from 0 to 14. So the reason why those numbers are there is because when the water dissociates, if I go over here and I go to water, notice what this says. I've got 1 times 10 to the minus 7 of hydronium ions and 1 times 10 to the minus 7 of hydroxide ions. So if I multiply these two together to get water, can you see I'm going to get 1 times 10 to the minus 14? And that is called the K, because it's an equilibrium constant. Remember, equilibrium is always the multiplication of the products divided by the reactants. Okay, so if I'm doing this equilibrium constant, so it's that times that concentration divided by the water. Now, water is a liquid. Will the concentration of water, pure water, change? Liquid water change for a fixed temperature? No. So just like the acids, just like the solubility, the KS that we did, where we could just ignore the solid, we can ignore the water. So we can write an equilibrium constant expression of K is equal to concentration of hydronium ions times the hydroxide ion concentration, and it'll always give you 1 times 10 to the minus 14. So how do you think we call that K? You've come across a KS, you've come across a KA, you've come across a KB. What do you think we'd call this? KW, right? So W for water. So you would always be given in a problem that the KW is 10 to the minus 14. Although by the time you've done a few problems, you would already know that. But that just sets the limits, and that's why your KAs and KBs will always multiply up to 10 to the minus 14. Yeah. Okay, so going back to, I think, oh, this is interesting. I just put this for interest. Remember we were talking about for a particular temperature. If we do room temperature, which should be 25, and calculate, let me clear it first, calculate. Then my pH, okay, there can you see KW. Let me just take it down to 20. No, okay. Should be 25. Okay. It's around about 1 times 10 to the minus 14. And we get a neutral pH. Now we always tend to think of a neutral pH as always a pH of 7. But that is only at standard temperature. Because remember, an equilibrium constant can change when the temperature changes. So if I crank down the water, so if you're thinking you're now going off to Southland or the Antarctica or something like that, and you're going to go into that water, okay, if I now calculate it, okay, it's actually slightly basic. So the colder the water, the more basic it is. Okay. And if I crank up the temperature and I calculate it, then it goes acidic. So if you were ever asked, true or false, the pH of the pH of neutral water is always 7, you can say, no it isn't, it depends on the temperature. Because a neutral substance just simply actually means equal amounts of hydronium and hydroxide ions. Actually, Johnny, you will still have equal amounts of hydronium and hydroxide ions as as um, as such. Oh no, hang on. Um, if I'm no, I'm going the wrong way around now. I'm thinking of if you're told it is neutral, then you'll have equal amounts of that. But yes, if you change the temperature, you're going to shift that where it lies. Okay. So let me just think this through. At a very high temperature, like 100 degrees, you still you can't really get more than one than the other. So neutral is going to be a pH of 6 at 100 degrees. Sorry, so I've been making go. Let's go to this equation again. You're still going to have this equation, but now what's going to happen is you're going to have, say, more of this lying towards the right when you increase the temperature. So you've actually got more hydronium ions present, so your pH goes up. pH goes down because you've got more hydronium ions present. And we base it on the hydronium ions. If we go the other way around, where was this? So if we have now a very cold temperature, then the equilibrium shifts the other way, and I have more water and less hydronium ions present, so my pH goes up, even though it's still neutral. Anyway, that's just as an aside. You can try and get your head around that, so I won't go back to that one now. Okay, no, I'm not going to do that one now. So going back here, what you need to be able to write are equations. So I think I'm just going to go to this, and I'm going to now draw. Now my handwriting isn't very good. So you need to be able to write equations for any acid or any base. So if I get given, say, ammonia, okay, and they may ask you a number of things about it. They could say, discuss its conductivity or the ions in solution. So the first thing you need to do with anything in this section is write the equation. That EQ method is important. So the equation is, because it's aqueous, you're always going to be reacting it with water. Okay? And it'll be in equilibrium. Because this is acting as a base, it's got to accept a proton. So if you're not sure what's going to happen, increase the level of hydrogens. It's accepting a proton. And at level 3, we just do the monoprotic ones. So add a proton to a base and subtract a proton from an acid. And then if I take away a proton, I'm taking the proton away from water, so I'm left with OH minus. Okay, so that is your equation. If I wanted to now discuss the conductivity, then I would say, well, the equilibrium lies more to the left, and so I'm going to have lots of, of this, and I'm not going to have very much of this over there. Okay, so I'm going to have a low conductivity and an alkaline pH, but not very alkaline. Okay, if they asked you to calculate something, they may say, for instance, calculate I do want to do an acid first, actually, so let me do an acid first. So, for example, if they asked you to now discuss ethanoic acid, then what you would do is write the same thing, but now it's an acid. So do I take away a proton or do I add a proton? You take away. And with the organic acids, is this correct? No. So remember it's always for the organic, the H that's attached to the O, because that's the polar bond, the OH. The CH bond is very hard to break. So let's get rid of that. Okay, and if I write then this, now is that correct? No, correct, because I forgot the charge. Always, always do a charge balance to make sure that you've added the negative for the anion and the positive for the cation. You won't even achieve that part of the question if you don't write the ions properly. By level 3, they expect you every single time to write the ions properly. Okay, so remember what I said with that EQ method, equation, expression, and then calculation. So say on this one, they said calculate the pH of a, let's make it an easy one, 0.1 mole per liter solution. And let's make it 00, because you always think of 3 significant figures. That's the other thing you need for excellence, is 3 significant figures. They do have to give you something else as well. So remember when you had to calculate the solubility and they had to give you the Ks, or they gave you the solubility and you calculated the Ks? You know, you've got to be given the equilibrium constant. So they would have to do it in some way. And they can either give you the Ka, or they can give it to you as the pKa. What do you think the pKa would be? The negative log of the Ka. Right, so just like if I have H plus concentration, then the pH is simply then the negative log of the H plus concentration. So the same thing, if I've got a Ka value, so say this is, I think it's 1.8 times 10 to the minus 5, then the pKa is just going to be the negative log of 1.8 times 10 to the minus, 10 to the minus 8. No, 10 to the minus 5. It's not important. I mean, you'd be given it. Okay, so if I was given the pKa, how would I convert that to a Ka? What would I have to do in my calculator? It's 10 to the negative pKa, correct. So if I have this and I was just doing the 1.8, I'm going to calculate first the pKa, exponential 5 minus, and log, so it's, and then I have to take the negative of it, so it's 4.74. So that's then equal to 4.74. So if you would, so you go divide by -1 and take the inverse log. Yes, that'll also work. So if you get given the pKa and you wanted to calculate the Ka, then you would just simply, let's just clear that, you could just say 10 to the, you know, and then it's 4.74 negative equals, oh, okay, then you go there. And there you get it back again, 1.8 times 10 to the minus 5. Okay, so practice, if you're not sure how to use your calculator, you know, keep practicing changing one to the other. Use simple values, you know, 1 times 10 to the minus 5, and then reversing that. Oops, okay, right, so say you had to calculate this. Now, with the EQ method, we've got the equation. The next thing is the expression. So we've got the Ka, I want it actually blue. We've got Ka, and Ka is the reactants multiplied together divided by the products multiplied together divided by the reactants. Now, do I have H3O plus in my equation over here? Does that equation have H3O plus in it? Yep. So we can use a Ka expression for that. So very quickly, CH3COO minus times H3O plus divided by, now my reactants. Do I include water? Does the concentration of water change? No, it doesn't. So we ignore it. That water term has actually been included in there. Okay, and that's why it's specifically called Ka. So now we have to calculate this. For every one of ethanoic acid that dissociates, am I going to get different amounts of those two, or am I going to get equal amounts of those two? Equal. So I can say here on the side, assume H3O plus is equal to CH3COO minus. Okay, so the same assumptions we did in the solubility. So can you see I can make that squared all over Does that sound sensible to you? I've made that equal to that, so I've squared it. So my Ka is going to then be 1.8 times 10 to the minus 5. I'm looking for the hydrogen ion concentration because I need to calculate the pH. And we are told what my ethanoic acid solution is. We are told it is 0.1. Now some of it has dissociated, but can we assume that because the Ka is pretty small, very little has dissociated? So really my ethanoic amount of ethanoic acid in solution is still 0.1. Can I make that assumption? Yep. So you can write that. So you can say assume CH3COO H is equal to 0.1. So I divide this by 0.1, and if it's divided by on this side, it's multiplying on that side. So it's 1.8 times 10 to the minus 6. Have I gone too fast for people with the maths? Because all I'm doing is I'm multiplying this by 0.1, so it's like dividing it by 10, so it goes up. And now you would have to take your square root. So because I want H3O plus, and I'm just seeing the time there, but can you see it's going to be the square root of 1.8 times 10 to the minus 6. And I should have left that open for the calculator. So I've got 1.8 exponential 6 minus, and I'm taking the square root. Okay. So you should get something like 0.0. If I've done this correctly, I'm just rushing it actually. Okay, 0.0134. Try and remember also to take at least 3 significant figures during your calculation. So 0.00134. Have I finished? Have I answered the question? Because this is moles per liter. Nope, I've got to do the pH. So pH is equal to the negative log of H plus, or hydronium ion. So it's a negative log of that. So if I now take negative and then log, it's 2.87. now take the negative, so it's 2.87. So, okay, because it is now 4 o'clock and I don't want to carry on for too long. But those are the sort of calculations you would be doing. So next time I'll do a KB, because a KB is slightly more complicated, and that's why I wanted to do a KA first. So it's, remember the equation first, so you know whether you are dealing with a KA or a KB. If you see a H3O plus in your equation, you know you can write a KA. Then it's just simply you write your reactants over your, your products over your reactants. So there it is. Change any pKa's to Ka's. Yep, includes, well, you would include states, perhaps if you were asked to write your equation up there. Caleb, do you need to, certainly for the solubility ones, it's, I don't think it's that important for these, but you should, as a rule of thumb for level 3, do it. Okay, because I know even like for the internals, for the redox, if you forget to write the, yep, so do it out of habit, because it does affect things if it's a gas, a liquid, or a solid. So then you just, as I said, it's the it's equation, the expression, and then you do the calculation. So there it is. I've gone slightly over time. And all the best, and I'll see you next week.